Okay, with this video I'm going to talk about trig identities, and this is extremely needed in the real world, and it's very helpful, and I'll talk about why we need it and what exactly are the trig identities and how do you apply it. So, when you look at a graph, you see something like this, this is a line. We could always say, oh, this is, y equals 2x, or whatever it is. And we could graph it as long as it's a line, However, we get problems when we try to graph something like this. Sorry about the lines. How do you graph that? Y equals, and this is the problems that we run into. Is graphing circular objects, things really curvy, and we figured out a way to tackle that is by using polar coordinates. Polar coordinates. And what is polar coordinates? Well, first let's look at our coordinates we're using right now, which is Cartesian or rectangular. So this is our coordinate system we're using right now. Y and x. If we want to get to this point right here, we go over x and we go up y. Boom. And that's how we get to this point. We always go over x, up y. Now, how does polar coordinates get to that same point? So let's say this is the same point as up here. Well, instead we go over a certain amount of degrees and we go up a radius. Now, what is the benefit of using polar coordinates as to Cartesian coordinates? Well, if you're on a boat or you're navigating somewhere and you want to get to this point, it's a lot harder to say, okay, well, I want you to get to 32, 33. I want you to get to the point 32, 33. And you're in the middle of a boat and you look at a map and you see where's 32, 33. Or you just or in polar coordinates you'd be like, okay, I want you to look 33 degrees and go up 1 mile. So you just turn your boat 33 degrees and go up a mile. That's the big thing about polar coordinates. It's a lot easier for navigation and it has a lot more perks than just that. So we're going to break down polar coordinates right now. So we're going to combine our polar and Cartesian coordinates. I don't know why I always put a wiggle in the middle of all my lines. Okay, so this point right here, to get there, you go over x, up y, or you go up a certain amount of degrees and across r. Now, this layout right here is extremely useful to understand what's going on right here. So, of course, there's two ways to get to the same point. X, y, or degrees, r. And we're going to talk about, and this is the right triangle. So we're going to talk about this relationship. So whenever you see a right triangle, go this way. This is the hypotenuse, which is across from the right angle. And it depends on where the degrees are going to be. So if the degrees right here, across from the degrees is considered opposite, and next to the degrees is considered adjacent. Now, of course, if you have the same triangle, this hypotenuse always stays here. But if the degrees are up here, then across from it is opposite, and next to it is adjacent. One thing to realize is that it must be right triangles every time. This does not work without right triangles. So I shall talk about the trig identities. So sine of theta, sine of this angle, is equal to the opposite over the hypotenuse. And remember, in our triangle, if I draw like this, we have theta right here. This is opposite. This is adjacent. This is hypotenuse. So if we look at this graph, we say, okay, well, sine of theta is equal to y over r. And we're going to look at cosine. It's equal to adjacent over hypotenuse, which is equal to x over r, adjacent over hypotenuse. And the tangent of theta is equal to the opposite over adjacent, which is equal to y over x. Opposite, adjacent. Okay, so these trig identities is all helpful and all, but you know, how do we apply them? So, I'm going to show a couple identities that we need to memorize, and you definitely need to memorize it. So to begin, if we said sine of theta equals y over r right here. So that means that if you get y by itself and multiply both sides by r, these cancel out and you get y equals r sine theta. Do the same thing for cosine and you get x equals r cosine theta. And we'll just keep tan like this, and tan theta equals y over x. And this is how you transfer from from Cartesian to polar. So if I have a graph like this, and I'm at this point, and this is 3, 0, then I plug in 3 for the x, I plug in 0 for the y, and I just solve and get my, that's how you translate over. So, besides that, I'm going to talk about the different identities we need to memorize. So, we have sine squared theta plus cosine squared of theta equals 1. And why does this work? Well, if we take sine theta, which is equal to y over r squared plus cosine theta is equal to x over r, so that equals 1. If we simplify this, we get y squared over r squared plus x squared over r squared equals 1. And if we multiply both sides by r squared, we get y squared plus x squared equals r squared, which is true because remember that's our graph right here. So according to the Pythagorean theorem, this is true. So of course we have this identity. Next we have another identity that you should memorize, which is 1 plus tangent squared theta is equal to secant squared theta. Alright, so these two are the major ones that you should probably memorize. There's another one where it's 1 plus cotangent squared theta equals cosecant squared theta. But overall, this is the main ones you have to memorize. So, how do we apply this? Well, for example, if we want to do a problem that says simplify cosecant theta minus sine theta. Now, this might seem a little tricky, but the main thing you have to realize is that each of these sine, cosine, and tangent, each of them has the inverse of each other. So sine, the inverse of sine, which is 1 over sine, right? So the inverse of it, 1 over sine, is equal to cosecant. And 1 over cosine is equal to secant. And 1 over tangent is equal to cotangent. Now this is a lot of material I'm covering for trig, but this is just an overview, and I could definitely get really into each problems, which I'm about to do soon. So we see cosecant, which is also equal to 1 over sine, minus sine theta. Now we gotta get like denominators to subtract them, because you need a common denominator. So for sine, we're going to multiply this by sine theta over sine theta. And why we do this is to get common denominators. So what happens is you get 1 over sine theta minus sine squared theta over sine theta. And this is just sine theta times sine theta sine squared over sine. Remember, when you multiply fractions, you multiply tops and bottoms. Now when you put this together, you get 1 minus sine squared theta over sine theta. Now, looking at this, it might be a little tricky, just because it's not exactly in our list. However, I'll move these out of the way. If you get cosine squared theta by itself, and you subtract sine squared theta on both sides, cosine squared theta equals 1 minus sine squared theta. And this is the identity itself. So when we look at this, we see this, and we're like, okay, well I can put cosine squared theta. So this is equal to, this is one big equal to, cosine squared theta over sine squared theta, sine theta. And you can break this up into two things, because this is also equal to cosine theta times cosine theta over sine theta, and cosine theta over sine theta is equal to cotangent theta cosine theta. Now some of you might be confused, where did cotangent come from? Well, if we know tan theta is equal to sine over cosine, then cotangent theta is equal to cosine over sine. Alright, so I decided that my next video I'm gonna do a bunch of these identities to try and get it stuck in your head, and you can do some practice afterwards. But I really want to get this identity thing down pat. So I'll see you next video.